So now let me explain one more time the so what we had discussed. So in the previous lecture that we have studied the attention encoding lecture that we have studied, okay, encoding is okay. So, okay, and this context vector, it is a summary of this input sequence. It's a compact representation, and when it will get generated, so the moment when you send the last word of the sequence, okay, now the context vector that will make a summary, clear, and this context vector, as it is a vector, so that is why it is called as a context vector, or it context means it reflects the meaning of, or it reflects the summary of this entire the sequence, okay, input sequence, input sentence, and this context vector that we will give as an input to this decoder again, that is a LSTM here, and the decoder will print the output in a step-by-step manner at t is equal to 1, okay, at t is equal to 2, t is equal to 3. So now this one is the encoder decoder architecture. Here, input, this one is the input sequence, turn off the light, okay, and H naught, that is the H naught, H1, H2, H3, H4, that these are the hidden state, that is the LSTM, okay. So hidden state, that is the short-term memory, and this cell state, hidden state, that everything that you know about this LSTM, and this one is the H1, and this one is also, that is the same, this H1. So the moment you send this last word of this input sequence, okay, this encoder generate a, one summary, okay, in the form of the context vector. The point is, the problem is, when you provide as a long sentence, okay, kind of one paragraph, this context vector that will get overloaded, okay, this all the load that will be on the context vector, because it is a kind of summary, clear. So the output of this decoder that will not generate the correct output, so that is the problem in encoder decoder. So now the mechanism that has been one developed, that we call as the attention mechanism, and the attention mechanism is, that is, you have to provide this extra input along with this S naught and this current input S1, and current input S2, and this current input likewise, okay. So that is the attention mechanism. So now for this CI, you have to calculate the alpha. Okay. So this one is a CI. So you have to calculate the alpha I or alpha ij. Okay. This alpha 1. So in place of this alpha 1, alpha 2, that I have written here in the form of the correct equation, alpha ij's. So alpha ij's, that is a function of this hj and si minus m1. So that I have written this equation here, this hj and si minus 1, and this alpha j, that is a vector, and si minus 1, that is again, both are the vector. So we have to calculate this alpha I j. Okay. So once you know this alpha I j, we can easily calculate this C1. Okay, CI, and CI, that is the extra, that is third input, just to print the output of the decoder at different time steps. So that is the attention mechanism. Okay, and this all this thing that we have covered, that is a one feed forward neural network. Okay, just this function, this alpha I, that is a function of this xj and si minus m1. Okay, so now we have to bring this this si minus m1. Okay, here actually, okay, this architecture of this decoder we have to change little bit, because the encoder that is over. Okay, once it generates the context level, part is over. So now we have to change little bit something in the architecture of the decoder so that it can generate the contextual word. Okay, so extra layers in this decoder, that is a feed forward neural network, the input layer, this hidden layer, and the output layer. Okay, so now this after this output layer, we have to pass the output of this neural network to the softmax. Okay, again it will generate the output, and that is a normalized output, and that is your finally that is CI. I hope this one is clear to all of you. So here that I explained this everything. Okay, just you one more time, just you go through this lecture. Okay, this handwritten notes, and further if you have any doubt or any issue, just you let me know in my through my just mail ID or this the group itself. So the next topic of the discussion is self attention. So now before start this session, this topic self attention. So I want to ask you a small question that what is the most important most important requirement for making any NLP application? For making any NLP application, what is the foremost important requirement? Okay, so now either you are doing sentiment analysis, okay, or doing named entity recognition, or doing the machine translation. Okay, for any NLP task, what is the most important requirement? So now the answer is the requirement is correct. So how do you convert the word into a number? How do you convert the words, okay, or that is a text into a number? So the computer that cannot understand the words, okay, what they understand number. Okay, so in the language of NLP, it is called the vectorization. It is called the vectorization. So how can you vectorize words or text? So the first work that was done in NLP is that is vectorization. We have to just convert the text into a number. So the first technique is that is one hot encoding that already that I explained, the one hot encoding, and you all know this one hot encoding very well, how to convert through this one hot encoding, how to convert text into a vector or as a set of number. Okay, so the point is this one hot encoding that is insufficient. Okay, means that is not as good. So the second improvement is bag of words. Okay, that was a slight improvement. Okay, so here the improvement is just you can have in a bag of words. Okay, means there is as the name suggests that is a bag of words. whether the word is there or not. Okay, so one word encoding that already I explained. So now the back of words, let me explain for a while this back of. So now that word, it check how many times that in back of word. Okay, so let's say word that we, let's say name my. This one is a one sentence, and second one, my name is Vikas. Yeah, correct. So you will write again your unique word. Okay. So unique word, that is my name is Surinder Vikas. So these are the unique words because this my name is that is repeated in this in the second sentence. So so the point is you have to hold each sentence, okay, and ask and tell me how many times did my appear in your sentence. Okay, so here my appeared twice. How many times the name appeared? Okay, clear. So first you write the unique word. So unique word that is a my name is Surendra Vikas. So that is this one for first sentence. For second sentence, this one is this one is the bag of word for second sentence, and four times 1 0, that is the bag of words of this my first sentence. Okay, so are you getting my point? So let's say one more time is, let's say this sentence, first sentence is, that is met, cat and met. Second is, that is cat, rat and rat. Okay, so first you have to write the unique word. Unique word is, that is met, rat and cat. So for first sentence, so that is 2 0 and 1. Now can you give me the bag of words for the second sentence? So 2, that is how many times the met appeared in the first sentence. Okay, this this 0, very good. 0 to 1, absolutely 0 to 1. Okay, so this 0, that is how many times the rat appeared in the first sentence, that is 0, and how many times the cat appeared in the first sentence, that is 1 time. Okay, this mat, how many times the mat appeared in the second sentence, so 0, so 0 to 1, 201, that is for first sentence, 0 to 1 for the second sentence. So one hot encoding that we know, bag of words that also that we know. But the real point is, when this technique, okay, that technique that we call as a word embedding. Okay, this word embedding. So when this technique came, so this word embedding is much more advanced than this all other existing technique. All existing means that is a one word encoding and this bag of words. Okay, so word embedding. This is word embedding. And this word embedding technique, it is able to convert word into a number in a much better way. Okay, because this word embedding have the power to capture the semantic meaning. So let me, this word embedding that has a power to capture the meaning of a word, so to capture the semantic meaning of word. So what does it mean, this semantic meaning? The meaning of this capturing this semantic meaning is that this word embedding, this convert into a number in such a way that meaning of the particular this word and in what kind of context it is generally used. Okay, that's it means uh, the point is in what kind of context this word is used. So the word embedding assign a one number. Okay, here for this word, the word embedding is will assign a number. This for this one, the word embedding that will assign a number based on what kind of context it is used. Okay, this sentence that is used in what context. So accordingly, it will assign a number. So let me explain in a by this example. Okay. Now let's take a very large training data set. Okay. Let's take a that is large training data set. Training data set means just you can consider as a Wikipedia article. Okay, so that is all Wikipedia article. We consider this as a this data set. Okay, so now you send this all this training data set to a neural network. So this, let's say this one is a neural network. So now this neural network understands this training data, this all Wikipedia article. Okay, this is the training data. So understand the context in which each word is used, and then it represents each word in the form of n-dimensional vector. So n-dimensional vector. So n-dimensional, it may be 256, it may be 512, it may be 1000, it may be anything. Okay, so let's say this output of the neural network is a 5-dimensional vector. 5-dimensional vector. That is output of this neural network. And input is, let's say one sentence that contains that is 5 or 6 words. Okay, and the output that is a 5-dimensional vector. So since we have so that how to explain this? Let's say take an example. So okay. So this one that is a 5-dimensional vector. Okay, let's say there is a one that is king, okay. And this king and this king is 5 items. Let's say 0.6. So 1. Okay, that is 0.5. That is let's say this one is 0.3, this one is let's say 0.9. Okay, this is the five dimensions. Okay, similarly, then we can represent that is like the same way that is a five dimensional. Okay, so now the interesting thing is that we are able to capture the semantic meaning of this word. So if two words are very similar, then their vector that will also similar. This king and this queen, that is look like a similar. That is king and queen. So it look like a similar. So their semantic meaning, that is, if the semantic meaning is clear, sorry, semantic meaning is same, then the vector that will also be the same. Yes. Yes. And the geometric, this idea behind this is that in this five dimensional space, this five dimension, this vector, here, the geometric meaning that is actually I cannot draw this five dimensional this vector. Okay, so I can draw only the two dimension. So in this five dimension space, okay, the vector of king and this vector of this queen, so both will be very similar and will be that is around that is that is same. Okay, so let's say we take another, let's say we take another word that is a cricketer. Okay, again that is a five dimensional vector, that is cricketer. And this cricketer is that is different than this king and queen. Okay, so the word, sorry, the vector of this cricketer is, and that will be entirely different than this king and queen. Okay, so that is the beauty of this word embedding. Actually, this word embedding, actually this technique is capture the semantic meaning of the word. Okay, so let's say if we go in more detail of this word embedding. Okay, so here this every dimension, this one, the every dimension that reveals some aspect according to your sentence, according to your word. So like the first this dimension, this one, the first dimension that may represent this royalty. Let's say. Okay, so obviously it is a king, so this factor that should be high, let's say 0.8. Okay, if it is queen, okay, so let's say 0.9. So if it is queen, that is again that is 0.9. So that is a royalty. So the first that this dimension, that is a royalty. Clear? So 0.9 and 0.9. So, but in case of the cricketer, this factor that will be low, that is 0.1. The second, this dimension, that may be this athlete. Yes, it's not the weight. So that is counting this is, let's say this athlete. So this dimension, that is, let's say it's a 256 dimension. Okay, let's say this one is that is stored in somewhere. So let's say that is a 300, that is dimension. So in that way, if let's say that is second dimension, that is athlete. Okay, so in this one, if it is a cricketer, so this will be second one, that is high, so 0.8. But here maybe that is 0.1 or that is 0.1. Okay, as this one is a queen, so this aspect that will be the low. Third, that is a human being. Okay, so human beings, so king and queen and this cricketer, that all are the human beings. So that may be so 0.8. So here is 0.8. Here that is also 0.8. Okay, so all these three that this all these three that will be this one height. So basically these dimensions that have a meaning, okay, which we cannot actually this understand. So because the neural network that does not tell us what that dimension is, okay, so the every dimension that has a meaning and the similarity of each dimension that is 0.8, 0.9, 0.1, 0.8, 0.8. Okay, so on the whole, the two very similar words that will have very similar looking vector and dissimilar word will have different looking vector. It's very simple. That is the main idea. If suppose five words are there and that has a almost same meaning, the vector that will also be the same. And if some of the this word, some vector, some word that is different, then the representation that will also be the different one. Means it capture the actual this contextual meaning. That is a word embedding. So this is the main idea. So now embedding are very powerful and it is very useful. But there is a problem with this embedding as well. The problem is the problem of this average meaning is this one, that is average mean. Okay, so the representation is static, not dynamic. This representation of a vector, okay, this word embedding, this representation is static representation, not dynamic. This one is the average. So let me explain this through an example. So let's say this first sentence is an apple a day keeps the doctor away. Okay. And the second is that is apple is healthy. And third is apple is better than orange. And the last one is the apple makes better phone. Okay. So now I have kept this intentionally in a way. Okay, this apple here, this apple and this apple. So here that is our neural network. So here is our training data. Okay, so here we are sending this input sentence, and inside this, okay, there is a neural network. Sorry, there is a kind of layer. Okay, here the middle layer, that is how I'm going to interesting symbol. Just we take the this two dimension. Okay, this one is, let's say here three number of node and two number of that is hidden layer. Clear? So this one is a two dimension. Let's say for example that is the two dimension, just to understand it. So this means that every that word in this training data, okay, that is focused on a this one, that is single, that is what, that is apple. This one. So in this two-dimensional this vector, this one is a two-dimensional vector. So the first dimension that will represent the taste, and second that is the technology. So the meaning is we are just rating each word according to the two things. So the first thing is how is it taste and how much technology, that is component, is there in the this sentence. So taste and technology. Okay. So I know it is not logical for this other sentence, but at least for apple, okay, this taste and technology, it is logical for this specific word of this apple. It is not just related to this doctor, okay, and it is not related to this better phone kind of, but it is logical just to understand this apple word first. So now the what is the meaning of this average? Average meaning? Average meaning. So when first sentence is feed into this neural network, that is the first sentence, then what did the neural network? Neural network understand if you read this sentence, this one, an apple a day keeps the doctor away, then it seems like apple is a food. This neural network that will understand through this sentence, okay, this apple is a food item, and so obviously the taste component, this one, that will be high. So let's say 0.7. Okay, and the technology component that will be 0, because from this sentence the neural network will get to know this is a food item, and this first one, that is a taste, for this part, it will give the high value 0.7, or it may be 0.8, let's say 0.7, and technology that is 0. So now for the second sentence, apple is healthy. So when you feed the second sentence to the neural network, okay, the apple is healthy. So again, the neural network that will understand this apple is a food item. So it must be related to the taste. So the vector item that will increase little bit more. So maybe that is 0.72. Okay, and the second one, that is technology, that is 0. So now after this one, first sentence, that is the vector, that is 0.72 and 0. So now when third sentence, if you feed this third sentence to a neural network, apple is better than orange. Again, it seems like the taste, okay. So it increased little bit. The value of this one, let's say 0.75, and the technology, that is 0. Now the point is fourth sentence. So when fourth sentence that comes, Apple make the better phone. So now this is a different context. And after reading this, it seems like the technology. It seems like a technology. The sentence is related to the technology, this Apple word. Okay. So here the weightage that will increase a little bit. So the weightage of this technology that will increase. Okay, and this will be some little bit decrease. So after this fourth sentence, okay, so 0.73 and 0.33. So now this one is a final. Then further, Okay, let's say the if the three statement was apple is better than yes. So here this apple is better than the orange. What's the question? Let me just check. If sentence was apple is better than blackberry, what will it take as a taste of technology? Blackberry that may be it considered as a food, okay, means that is a fruit, okay, or it may be considered as a technology also. Again, that is the issue in the this word embedding, that is in NLP. So there are many more things that will come. Okay, so there are many more examples. So let me explain this here. Uh, so buffalo, and one more buffalo. So buffalo, that is the name of the university also. Okay, and that is a buffalo. That is the animal. Okay, and say that is will, will, will. Okay, and this will, that is a noun. Okay, let's say this one is a noun. This one is a will. Uh, wasiyat, okay, and this one is a helping verb, that is will. So the network, that what understand the network is, so again depends on the training, okay, so that is the thing. So the neural network, that again that will confuse. So in that way, so we have to just train the model in a better way. So let me explain this. Yes, data set. Correct. So this one is 0.73 and 0.33. So now this one is a fixed, that is a static representation. So this static, this 0.73 and 0.33 is for this first apple, 0.73 and 0.33 is for the second apple, for third apple, and for fourth apple. Okay. Sentences. So out of which apple, that as a fruit, that comes in 9,000. Okay, in 9,000 sentence, and Apple, that as a phone company, that come in a 1,000 sentence. So then obviously the overall this vector that will be formed will probably look like something 0.9 and 0.3. This one apple as a fruit. Okay, so now that is 9,000, and this 1,000, that is as a company. So it depends upon the data set. So it depends on the data set. That is the average meaning of the apple. Okay, so average meaning of the apple, this word in this whole data set, as a fruit is more. This apple, this word as a fruit in this whole data set, that is more. Okay, so that it depends upon the data also. So am I clear to you? Okay, thank you. So I am just trying to say that how the word embedding will look depend on your data set. So because the word embedding is basically the average meaning of a particular word. Okay, so that is average meaning. So that is the problem. So the word embedding are created once and are used all the time for each word. Okay, that is this one 0.9 and 0.3. This one is a static. Once this word embedding of this apple is created, now I am going to use the same word embedding. Okay, same word embedding everywhere. So now this is the problem. This static representation. Okay, that is average. Average one, that is this one is a problem. So this, let me explain this through an example. So suppose I am creating a small NLP application where job is to perform to translate the sentence from this English to, let's say, Hindi. Okay, and let's say that I have given a sentence: Apple launched a new phone while I was eating an orange. Here. Okay. So the sentence is, that is, we will give this sentence to a neural network. Apple launched a new phone while I was eating an orange. So we have to convert this sentence into Hindi. So what will you do first? You will convert all this word into their respective embedding. So now the problem arises. What is the embedding of Apple? Is 0.9 and 0.3. And this embedding is a static. And this assume that wherever apple is being used, it will be fruit only, but you can see from this sentence, Apple is actually used as a phone company. It's a technology. So ideally, it should be this contextual embedding instead of this static embedding. So contextual embedding means it should be 0.3 and 0.9. This one is a contextual embedding, and this one is a kind of, this one change the dynamically based on the text. This one is much better because it's dynamic. But this one is, it should be 0.3 and 0.9, and the network should be smart enough that it should not get confused with this orange, because orange is being used in this sentence as a proof. Yes or no? So to solve this kind of the problem in this, uh, this static representation, okay, just to solve this problem, that we use the self attention. Okay, so this problem that we can solve through this self attention. So self attention, this one is a model of self attention. Okay, so this self attention is such a mechanism that generates smart contextual embedding from this word embedding. Let's say this one is a word embedding. That means you can consider self attention that as a function where just you send this entire the sequence of this input, okay, to this self attention model means uh, this one, okay, let's say this one is the self attention model. So now this as an input, this one as an input, this one is input, and, and and this one is also an input. Okay, so if attention, that is a 4-5 sentence. So first sentence, okay, much better than all. And output, there is some calculation that will run inside, and due to which, okay, you will get a new embedding, that is F1. Okay, so one this kind of vector representation, and this final, that is a smart, this contextual, this embedding, and this further just you use in next model or like this architecture like transformer. Okay, that is a smart contextual embedding. Not this one is a static word embedding. So now the summary is this self attention is a kind of mechanism that can take the static embedding as an input and generate the good smart contextual embedding. Okay, so which are much better to use for any kind of NLP application. Okay, so let's say the example that is money bank, or that is river bank. So for this bank, okay, so for this bank, let's say this one is 0, 0.1 and 0.7, the based on the data set. Okay, so if this bank is coming in context of a money, then embedding that must be some other number. And if this bank is coming in the context of this river, then it should be different than this bank. Okay, means it should change dynamically. And this problem that is solved by this self-attention. So this converts the static embedding to a dynamic contextual embedding. Clear? So now let me explain what is inside in this self-attention. How it converts this static word embedding into the contextual embedding vector. Clear? So now the flow diagram of this self-attention in transformer is kind of this one. That is a self-attention. Okay, let's say the sentence is human love smartphone. Okay, and this one is the word embedding. This one is a word embedding for this love. This is one. There's a word embedding for this smartphone. Okay, this one is a E1, this one is a E2, this one is a E3. And this static word embedding, that is a form of the input in this self-attention, and the output, that is a smart contextual representation. Okay, so this one is a y1, this one is a y2, this one is a y3. So now question is how self-attention works. So first of all, you can do the static analysis of this three word. Okay, maybe from any of the technique of the word embedding. Okay, so you can use word to word, you can use whatever with the embedding technique. Okay, so you send it to the self-attention block. This self-attention block will do some calculation internally, and on the basis of the calculation here inside in the self-attention, for every static word embedding, it generated dynamic contextual embedding. So let's say the example is money, bank, grows, and here the river, bank, flows. Okay, so these two sentences actually these two sentences they does not have any meaning. It is good to listen because they are kind of the rhyming sentence. Money, bank grows, river, bank flows. That's it. Okay, so there is no technical meaning of this sentence one and sentence two. Okay, but it is good to listen these two sentences, and that's it. So now point is that is bank. Okay, this one, and this is in a different context, and this one is in different context. Okay, so now let us understand what is happening inside in the self attention block here. This one. Okay, so now up to so far, is there any doubt? Okay, so now this bank, okay, even though these are the same word, this bank and bank, but in different context. Here that is money, here that is river. So I don't think the meaning of both of these words that is same. So let me put this my mind to it, that I will say that I don't write bank this like a bank. I will write to the bank in this manner, that the bank is made up of this little bit of money, little bit of this bank, and little bit of this growth. I should not write, I should not consider this bank as a bank, as a single entity. Okay, so I should take some little bit concept from this money. I should take little bit concept from this bank, and I should take the little bit concept from this growth. Okay, so now the first sentence is, that is first sentence, that is bank. So 0.3 of money plus 0.6 of bank plus 0.1 grows. Okay, for second sentence, the bank, that is 0.5, that is river, plus 0.4, that is bank, and plus 0.1, that is flows. Okay, so now it depends on the context. So meaning is, I would represent like, so this money is 0.7 money is the example, 0.2 that is bank, plus 0.1, that is growth. Okay, and bank, this is for first sentence, 0.25 money plus 0.7 times of this bank plus 0.05 times of this gross, and this gross is equal to 0.1 times of money plus 0.2 times of bank plus 0.7 times of this growth. This is an example. I can take anything in this scalar value. And for second sentence, that is river, bank flows. So here that is 0.8, that is a river, plus 0.15, that is a bank, and plus 0.05, that is flows. And 0. Actually, let me write this complete thing, then only you just understand the concept of this self-attention and flows. And the last one is 0.4, that is a river, plus 0.01 for this bank, and plus 0.59, that is for. So the benefit of this is to focus on this both of the uh, of 0.1 of primary, 0.2 this one is a medical sentence. Okay. So actually that is the kind of self-attention. So there are many more things that will come inside this self-attention mechanism. Okay. So now the softness, okay, that will come inside this one, and there are many more things that will come. Okay, that is a part of this whole this understanding of this term. Okay, okay. Then why it is called the this self attention and how it is analogous mechanism. Uh, in the last session. Uh, okay, so if you have any doubt till now, then you please write in a chat box. because the next there will be another session at 12:30. So maybe the rest part of this self-attention that I will explain in some other day. Okay, so up to so far that if you have any doubt, any question regarding this self-attention, this attention mechanism and this encoder decoder, then you please let me know or write in a chat box. Okay, so if you don't have any doubt, then we can wind up the session here and let's take a 5-minute break. Then the next session that we will start at 12:30. Is it fine? Okay, okay, fine. So thank you all for listening this lecture. So now let's take a 5-minute break so that we will start the next session at 12:30. Okay, thank you. Thank you very much.
Thank you, sir.
Thank you, sir.